Okay. Do you guys hear me well? Because I already asked that. But people say yes. Okay, thank you. All right. So we haven't covered signatures, and actually signatures is also a good way to lead to zero knowledge. So today, what might be, we'll see if how far we get, but I will define signature. So understand what a signature is supposed to do. Show how to go from RSA assumptions to secure signature. And introduce, we'll see how far we get, zero knowledge proofs. And if possible, then also show that zero knowledge proof and in general, a one-way function gives you gives you a signature. You can create signatures from just one-way functions. Zero knowledge proof speeds it up, and it's actually very efficient in random oracle model. And in particular, DSA and ECDSA are the standard signature schemes that in fact follow this path. Okay, well, not exactly. They a little bit veer from the path, but this is not exactly how these signatures are created, but still, this way of explaining them, I think, is the most general useful in general way. Okay, so let's jump to it. What is a signature scheme? So a signature scheme is a tuple of algorithms generate a key, sign, and verify. Okay. On some message space M, okay, best, of course, is that if the message space simply includes all bit strings, but that might not be achieved at first. So the semantics of these algorithms that keygen on input a security parameter creates a secret key public key pair. A signature algorithm takes the secret key and a message and creates a sigma. This is a signature. And a verify algorithm takes the public key, a message, and a purported signature and outputs 1 or 0. 1 means accept, 0 means reject. Okay. So a signature scheme is basically like a message authenticating code, but with public verification. Okay, so the difference is here. In a MAC scheme, you picked a single key, and the same key was used to create MACs and to verify MACs, right? It was a symmetric scheme between Alice and Bob to authenticate messages based on a shared key. And now, in order to verify, you don't need to know the secret key. And in fact, a secret key can be created together with an accompanying public key, which can be distributed to the whole world, and everybody will be able to run this verification algorithm. And only you, the holder of the corresponding secret key, will be able to run the signing algorithm. So, well, correctness is sort of the obvious property that for every secret key public key generated by the keygen for every message in a message space. Sometimes the message space might be associated with the public key. So maybe this message function is a message space is a function of the public key. This will be the case in RSA. If sigma is generated, is output by the signing algorithm on the secret key and a message, then the verification on public key M and sigma outputs 1. Okay? In other words, verification of the correct signature accept. What about security? So let me just jump to the chase and give the strongest security that we expect of these things, which is the chosen message attack CMA security. So chosen unforgeability. And actually, this type of unforgeability also has a name. It's existential unforgeability in the sense that you don't need to forge message on any particular signatures on any particular message. Existence of any message on which you can forge signatures suffices for the attack. So what is this? For every efficient algorithms probability that B is 1 in following game, which will be called the CMA game of a signature, is negligible. And what's the game? So the game first picks the private public key pair for a given security parameter, tells what's the public key to the attacker. The attacker asks, please sign the following message, any message of his choice, and what he gets back is a signature. So every time he asks for the signing of anything, we generate a signature using the sign algorithm and return it to him. And he can recurse that, right? So this goes for I equals 1 to Q, which is a polynomial in a security parameter. Okay. And finally, he's outputting some message purported signature pair, and he wins. So we set bit to 1 if first of all, the message is new, so M star is not MI for all I, right? And secondly, the verification on the public key and this thing worked, right? So if these conditions are satisfied, then we call M star sigma star is a signature forgery, right? Because these sigma i's are the game, yes, plays the role of an honest player who picked their secret public key and, obligingly signed Q messages of adversary's choice, right? And this model is an arbitrary application, which sort of forces you to sign whatever it is that the application wants. Okay, you have no control over these applications. You don't know what you're signing, and you're signing according to what application tells you. But what should happen is that no one, even though they could choose the application and get to see the signatures you create, is going to create anything that looks like message that is different from the ones you signed, and a signature that actually verifies, right? That tuple is, if they manage, this is called signature forgery, and of course, the notion of unforgeability says that this attack is can only occur with negligible probability, right? Again, what is new here? It's this part, right? So this is not in a MAC scheme, right? So everything else basically could be like in a MAC. This is just a symmetric key, and the same key is used for verification. The difference is adversary gets to see the verification key, right? And in spite of that, the MAC, if you should remain unforgeable. So for a while, people thought that it's almost like a contradiction that a proof of security of any signature scheme that it would survive this is almost like a contradiction, because look what the proof would have to do. You're trying to, the proof for any scheme based on some cryptographic assumption would have to, this would be played by, this part will be played, will be emulated by reduction, which, given some hard problem, will be able to extract solution to this hard problem given a forgery against the signature scheme, right? So the reduction will be somehow able to translate this into, okay, if you could sign, then the only way to create forgeries is to compute discrete logarithms, say. So the reduction, given the forgery, will be able to compute discrete logarithm of some challenge. But how could such a reduction be possible if the reduction itself needs to compute these signatures on any other message? So somehow it needs to convert some hard challenge problem into the solution for that problem if adversary forges, but the reduction has to, in some sense, forge itself, right? Because if the reduction knew the solution to the hard problem, if the solution to the hard problem was the ability to sign, then therefore the reduction needs this solution in order to be able to sign, because it's signing right there. So how come there can be any algorithm such that you can solve a hard problem while emulating signatures on anything adversary asks, but when he proposes some signature on something new, then you can nevertheless extract a solution to the harder problem from this? It really looked like there is no way to do that, right? It's a contradiction in terms. So you can see the book, Katz-Lendl. It sort of guides you through signature scheme. It can be actually gotten from any one-way function. So even from a symmetric crypto, right? Because if you remember, one-way function is something implied by even a pseudorandom generator. And so basically anything in a symmetric cryptography already gives you a one-way function. So it's, in particular, it's very easy to create a one-way function from symmetric cipher, block cipher, or collision-resistant hash, which is all the tools that we use to create all the symmetric cryptos from. And in particular, you can use any of this to sign. So you could use MD5 or SHA hash. You could use block ciphers to create a signature scheme. This signature scheme will be stateful, and then it's like a complicated way to make it unstateful. And you can see it's a sort of a theoretical result. It's not like quite, but on the other hand, it's a return to this, because signatures from either discrete log or RSA are broken by quantum algorithms, whereas these generic constructions not. Okay, so so there is, there is still, might appear theoretical, but actually it's interesting and could be, could be used in practice for example, quantum security reasons. What I will give you here first is that RSA plus random oracle model on hash function gives you secure, so CMA secure signatures. Okay. So let's look what's RSA. So RSA is really something called trapdoor permutation. I introduced this as RSA as an encryption, but really it's something more fundamental called trapdoor permutation. And what's a trapdoor permutation? This is like one-way permutation, but with a trapdoor. Okay. The trapdoor permutation has a key generation, eval, and invert, and a message space. Okay, again. Okay. So key generation on a security parameter creates, and you can these things were called differently in for example, in Katz-Lindell. I'm just going to call them secret key and public key. Okay, and typically the public key defines a message space, so this is the key generation algorithm has this input, and the secret key and a public public key defines message space M PK and function which we can tag by the public key, right? Because it defines this function, which is a permutation on the message space. And it's a one-to-one function. Okay, and eval, it's an efficient algorithm which, given a public key and a message, let's call it X, in the space. So this is actually not called message space for trapdoor permutations. It's called like domain. Okay, so this is domain of this function. Okay, it basically outputs the value of this function. Okay, it evaluates this function. Inverse has the secret key and a value of the function and outputs X such that function on X is Y. In other words, X is the inverse of this function applied to Y. So this function is an inverse of FPK, right? And that's what the inversion algorithm computes. The parlance of trapdoor permutation is that this thing is called a trapdoor. Okay, so the public key defines a function, and everybody can run this evaluation algorithm given the public key efficiently to evaluate the function forward. But in order to evaluate the function backward, in other words, to evaluate the inverse of the function, I need a special information called a trapdoor, which here I simply designate as a secret key. Okay, so the correctness is, of course, if you generate this correctly, that if you evaluate it forward on eval, then if you evaluate it backward using the inverse, you're getting the same thing. Okay. But security is that FPK is a one-way permutation even in the presence. It's basically that FPK is a one-way permutation. In other words, for any efficient algorithm, probability that if this algorithm gets the PK and gets a value y, if he is trying to compute x, that will be negligible. Where this comes from? So secret key, public key. So in other words, the function instance was created by a key generation algorithm, right? So it's randomized generation of this. And then X was sampled at random from the message space associated with this public key. So I sampled the random point here, and I evaluated. So Y is an evaluation applied to PK and X. Right? So in other words, first the attacker, secret key and public key was generated, and the public key attacker has. Then I sampled at random a point X and gave the attacker Y FPK of X. And I asked him what's X, and he should have a low probability of outputting this, right? Given these two inputs. That's the one-wayness, right? So one-wayness of a function is that I pick random elements in the domain, I give values, and efficient algorithm cannot invert. Here, what's the difference is that there is an associated trapdoor. So somebody who holds this trapdoor can invert. So in particular, if I give you the description, the public description of the function that allows efficient evaluation of the function in a forward direction, you cannot decipher this secret key, because if you did, then you would trivially just apply the inverse to the Y and the trapdoor to compute X. The RSA assumption is essentially, it's exactly the assumption that the RSA function is a secure trapdoor permutation. Okay, so that is the RSA assumption. Okay, and now what is the RSA function? So the keygen that creates RSA function. So here is what I mean by RSA function. And by the way, if you want to be more specific, for a fixed E, we define, it basically is an RSA assumption for a specific E, and then I will define an RSA function for a specific E. So what is this function? On a security parameter, it generates skpk, where sk is a pair of primes, p and q, random primes, right? So I'm not going to go over all the math of RSA, but the secret key were 2 primes, and the public key was n and e, such that n was the product of these 2 primes. Okay, and we needed these 2 primes also to satisfy that the GCD between e. Now I don't know what I was saying. Okay, let me erase this. So P and Q are random primes. GCD of E and phi of n has to be 1, right? And just a reminder, phi of n is p minus 1 times q minus 1. And SK is, we call it D, and it is a multiplicative inverse of E modulo phi of n. Right? And because E and phi of n are coprime, so this multiplicative inverse exists, and this is the trapdoor. Okay, and now what's the function? FPK. Okay, so first, what is the message space? The message space associated with the public E n is Zn star. Okay, so again, what was the Zn star? Is all values modulo n, which are coprime with the modulus. Okay, so FPK is a function from Zn star. It's a one-to-one function permutation. I mean, it's a permutation on Zn star. Defined as f and e of x is x to the e. Just exponentiation by a fixed exponent e. And the inverse of this function the inverse function on y, outputted y to the d. Right? And last time we checked that these two functions are inverses of each other. So if you exponentiate to the e something, and then take that to the d, you get x to the e times d, but mod phi of n, because that's the modulus that works on in the exponent. But d and e are set so that d times e mod phi of n is 1. So therefore, x to the ed is really x to the 1. So therefore, it's x. So that's the proof that this function inverts that one. Right? We did it last time. The RSA assumption is that this particular function is a trapdoor permutation. In other words, that this function is a one-way function. So that's exactly how we defined the RSA assumption last time. We said RSA assumption is if you follow this procedure for generating SK-PK pair. So PK is NE, and SK is this associated trap. So you give RSA public key NE to the attacker, and you sample a random X in the space of this space, and you give him X to the E, and you ask him to give you X, right? So his goal is to compute ETH root mod n. And the RSA assumption is that this is hard, right? We discussed it last time. You can, for like, what's the evidence that computing ETH root should be hard? Okay, but this assumption still stands, and it's the basis of RSA cryptosystems. Okay, so let's look. How do you use this assumption, this type of thing to sign? So now you can think of the instantiation of this as an RSA, right? So the function is taking ETH powers mod n. The inverse is taking these powers mod n, which is equivalent to taking ETH roots mod n. Okay, and assume that taking ETH power is a one-way function. Okay, so how could you use it to sign? So first, let's do something that is called a textbook RSA signature. the public key is like in RSA, right? E times D is 1 mod file then. The message space is Z and star. So the domain of this one-way permutation, of this trapdoor permutation. And how about when I sign using, in a signature scheme, I sign using the secret key and I verify using the public key. So, you can see that just compare the setup between what's a trapdoor permutation and what's a signature. Keys, the same. In what can you do with the public key? You evaluate the trapdoor permutation. What can you do with the secret key? You invert that one-way permutation. Okay, so let signing be inversion of the one-way permutation on this element. And let verification be computing the same function forward on this element and checking that this inversion was correct, right? So that is indeed the RSA signature, the textbook RSA signature. You given the secret key and a message, output signature such that signature is the inversion using the secret key of this message. In other words, what did I compute? The function inverse applied to point M. And let the verification algorithm on public key and M sigma output 1 if and only if, okay, so message is here and there is this FPK function, right? So given a public key, everybody can compute this function forward, but this inversion, FPK inverse, possible only with the trapdoor escape, right? So we signed by treating message as an element, as an output of this function and inverting it, right? So this was our signature. So what are we doing to verify? Well, we just compute the function forward on the signature. So in other words, if a val on a public key and a signature gives out the message, right? Which is the same as to say that applying the function forward to the signature gives us the message. Okay. So for RSA, this in fact, it's really from any trapdoor permutation. It's there was nothing sort of specific about RSA, right? Like if you have any trapdoor permutation, you can do the same thing. You sign by inverting it and verify by computing it forward. So for RSA, the signature using D and M would be just M to the D mod N, right? Because that's the inverse function, right? So the inverse function is computed to the trapdoor. I mean, right? Exponentiate to the trapdoor. And verification on a public key, which is any message and a signature, outputs 1 if the forward direction works. And what's the forward direction? It's X to the E. X is the signature. So if sigma to the E is message mod N, right? So in RSA's parlance, encrypt is like verify, right? Because this was the same function that we used for encryption. And decrypt is for sign. Okay. That is not, this correspondence between some encryption scheme and some signature scheme is not universal. But the textbook RSA encryption and a textbook RSA signature are in this relation. Okay, so here is and let's just recall what it is that we would like to show about it, right? What we would like is that if adversary gets a public key and he can ask for signatures, he cannot produce a forgery. What's the forgery here? It's some pair M sigma, which is in this relation, right? Any M sigma, which is in this relation. So I tell you that like adversary doesn't even have to ask for any signature, message signature pairs. He can immediately create M sigma, M star, sigma star, which will satisfy this verification equation. Because M star, sigma star satisfies as long as FPK, which is publicly evaluatable on sigma star, equals M star. So textbook RSA is insecure even to no message attack. It was supposed to be secure. I mean, what we want is chosen message attack. So adversary can ask any message and get a signature on it. In fact, it's not secure. Even adversary can skip this. So there exists efficient algorithm such that A, given the public key, outputs M star sigma star such that verification on M star sigma star is 1. So what has to happen for the verification to output 1, where the verification is like this? So because this is the same as to say that evaluation of this public key function on sigma star is M star. You see, this is how we constructed the signature scheme, right? This is the verification. So it's absolutely trivial to create such a pair. Okay, since we don't have like a great communication channel, okay, let me, how about you just write on a chat? So attacker given PK, how can he create this pair? Can he create this pair? Just write on the chat, like what does he do? I'm still waiting. if the question is not clear, the attacker is getting a public description of the function. The function is efficiently evaluatable given this description. And all the attacker needs to do is an argument and a value. And that's already a forgery. Yeah, exactly. So what does they do? A on PK picks any sigma in the message space and sets M to be the FPK of sigma. And voila, he's done, right? It's insecure for other reasons than this. In particular, this function is homomorphic. So another reason is that FPK is multi-homomorphic. What does it mean? If I multiply the values of this function on two elements, then I get the value of the function on the product, where all these modes are both mod n. Okay. So you can check, because this is x1 times x2 to the e mod n, and this is x1 to the e, and this is x2 to the e, and this is a mod. So these two are the same, right? Because this exponentiation is mod n, this exponentiation is mod n, the moles is also mod n, so it's the same thing. Why would that be bad? Because this implies that from a signature on M1 and a signature on M2, you're going to get a signature on, for example, M1 times M2, right? Because the so FPK is homomorphic. Also, the inverse is homomorphic in the same way. Right? So the inverse function takes everything to the d, but that doesn't change anything, right? Like so. Computing inverse functions on these values, right? So signature computes the inverse function, and it's multiplically homomorphic, right? So in fact, basically, because you can multiply x by itself, right? So you have the value, the inverse on x and the inverse of the same x, you got an inverse on 2x, like x squared, right? So this you can generalize to any powers for any alpha beta, right? Because you could just multiply by itself to get this. So that's another reason, right? Like so given signatures on some m, I basically can generate many signatures on some other m's that are related to this one. So how on earth I'm going to change it into a signature scheme if it has all these attacks? Well, let's just observe one thing. This attack is, devastating against existential unforgeability, So the existential unforgeability said, you know, you attack if you create any message signature pair that is accepted. However, adversary doesn't have like a great control over what message it is creating a signature for, right? So in this attack, picking any, well, you know, so maybe he picks at random. Well, so the message is also a random value. Well, he doesn't have to pick these at random, but in a sense, this attack algorithm is kind of, you know, pick some element in the space, compute the function forward, and see what you get. In practice, you know, you would like to sign something useful, right? And if that something useful was somehow massaged so that a signature on a useful thing would have to be a signature on a random challenge thing. So a random message, a valid message is encoded in such a way that it's a random point in the domain. Then in order to forge a signature on it, I have to invert this function on a random point, right? So remember, what was the assumption? The assumption was that the FPK is a one-way permutation. It's a one-way permutation with a trapdoor, so trapdoor permutation. That if somebody sampled random points here, no attacker can invert. So in some sense, we have to do two moves. Encode the message, like say, okay, a valid message signature has to somehow invert at a point that is related to the message, but somehow randomized, so it's a random point. And a second part that we have to do is to show that in spite of these random encodings, there is a reduction that will be able to create these fake signatures, so to speak. And anything new that is not equal to that, if he inverts, then he can attack. Well, the random, we will use the random hash function to accomplish both, to randomize the point that is being signed and to enable the reduction to fake sign for any message that is requested, that the adversary requests. So here is the CMA secure signature from RSA. In fact, any trapdoor permutation and random oracle hash onto the message space of this trapdoor permutation. Okay. So Lec18 be a hash function that takes any bit string and outputs elements that are random in the n star, where n is chosen by RSA key generation. Okay, to RSA trapdoor permutation key generation. So this is really H should be indexed by n, right? Because how on earth, you know, for any n, some fixed hash function is not going to give you random outputs in this range. Okay. In fact, you can take a fixed random hash that you believe outputs, you know, random 512 strings or you know 256-bit strings, and you massage it for any n so that the outputs actually sample maybe not at random from here, but from a distribution that is indistinguishable from random in here. But we'll skip this, okay? Okay, just assume that you can hash onto this space and that this hash function is indistinguishable from a random oracle. Okay, then the key generation is like it's the same as the RSA trapdoor permutation key gen. Okay, so the public key is NE, the secret key is D, blah blah blah. Okay. Now the message space is any bit string. And in order to sign using the secret key and a message, you output sigma such that sigma is the inversion of this one-way permutation applied to point x, where x is hash of the message. Okay, so in other words, in the RSA case, the RSA case of the trapdoor permutation, sigma is hash of m to the d mod n. Okay, because that's the inverse function is exponentiating to the d mod n, and the point at which you evaluated is the hash of m. Okay, and verification given public key message and signature outputs 1 if and only if evaluating the function forward on a signature gives me hash of m. Okay, so in RSA that would be that sigma to the e is hash of m mod n. Okay. Why is this unforgeable signature? This version of RSA is called full domain hash RSA, abbreviated FDH-RSA. That's the name of this construction. Okay, and you can see why it's called full domain hash, because that's how we're using the hash function. We are using the hash function to map a bit string that we want to sign onto the domain of the trapdoor RSA trapdoor permutation. And so the hash function does the job of sampling, because it's a random function, so it samples a random point in the domain of the trapdoor permutation. And then the signature is inversion of the trapdoor permutation on that point sampled by the hash function given a message. And you compute forward and you check that this is indeed the point that was given by the hash function. Okay. The difference between the textbook where was this textbook RSA, right? The difference between the textbook RSA is when I verify, I compute the function forward. So these 2 points are, very similar, right? But I expect to see not the message itself, but the hash of the message. And when I signed, I compute the inverse, not at the message itself, but on the hash of the message, right? So it's a hash function that is doing this randomized encoding of a point of a message as a point in the message space, as in the domain of the trapdoor permutation. So how come that the textbook RSA that had so many insecurities, they're not only all taken care of by this sort of simple trick of signing a hash. By the way, it's a very natural trick, right? Because we want to sign messages not in with a formed in some strange way. We want to assign arbitrary bit strings. So it's very natural. Take that bit string, hash it into an element in this space, and sign that. And it has to be a collision-resistant hash, right? You don't want two messages to hash in the same way, because then a signature on one would immediately imply a signature on the other. Well, a random oracle hash is collision-resistant, right? It just outputs random elements in this space, so it's collision resistance, with the birthday bound. So it's a very natural construction, and actually, if you take this very strong assumption that the hash function is like a random oracle, then you're done with all security concerns. So maybe intuitively, let's see, how come these particular attacks are no longer valid, right? Well, so try to do the same here. So you pick any element in the message space and you compute forward. Well, this no longer works, right? Because you have to, if I pick a random any sigma star and compute it forward, now I have to invert the hash function. And the hash function is a random oracle. So I'm unlikely, right? It's not only collision resistant, it's actually thank you. Okay. Sorry about that. So okay, what happened? So at some point I was disconnected, okay, but I'm not sure at what point. So I was saying that these particular attacks no longer work, right? And I don't know if that went true, that this attack where you just take a point in the message space, compute this function forward, but now if you do that, right, you have to expect that the result, well, you have to find a message that hashes onto that result. And the hash function is a random oracle, so in particular, it's one way. So that's unlikely. You can hash different messages, but you're only going to do polynomially many. The domain of the message of this trapdoor permutation is large. Yes, otherwise it couldn't be a trapdoor permutation, right? Because you could invert things by just randomly picking the elements in the domain and computing forward, right? So, so having a small fraction of values pre-hashed, it doesn't mean that when you do this forward, you're going to hit any of them. Well, and this hash function also breaks these homomorphic properties. right? Because now this signature on M is an inverse applied to the hash of M. A signature on M2 is an inverse applied to hash of M2. So what you're going to get by multiplying the two is the inverse applied to hash of M1 times hash of M2. But that basically has nothing to do with the hash of M1 times M2, right? So the hash of M1, hash of M2, and the hash of some sort of combination of M1 and M2 are no longer related if the hashes are narrow. So these are intuitions. We see that that these attacks no longer work. Okay, but how about the proof of security? Security proof by reduction from CMA attack to trapdoor permutation inversion break. So the reduction is getting a trapdoor. So what's a trapdoor permutation experiment? Here it is. Somebody picked an instance of the trapdoor permutation, gave us the public key, and also they chose a random element in the space. They evaluated the function on this point, and they gave us the evaluation. And the reduction's job is to create X such that it inverts the function on the challenge point Y. Whom does it have on the other side? Well, it has an attacker that supposedly breaks the CMA security of this signature scheme. So first of all, he gets the public key. Well, it's the same public key as the trapdoor permutation. And given when he asks for a message, for a signature on a message, we have to sign it. But what's a signature? Well, a signature is an inversion at a random point. So we somehow have to create a signature such that if you apply the function forward, so FPK applied to sigma I is the same as hash of mi. You know what? I need to write it bigger. The reduction has to send sigma I such that the function forward applied to sigma I is hash of mi. And this can go on for I1 to Q, right? That's the notion of the signature scheme. CMA security. Finally, attacker creates M star sigma star, and let's say that he is successful. So if he is successful, meaning that the verification works, well, what does it mean that verification works? So FPK applied to sigma star must be hash of M star. Then R should somehow get X. Okay, well, so let's just assume this. So if this is true, if this, then A wins. And we want the reduction to win at the same time, right, in its game. But another thing that A does, we are in a random oracle model for this hash function. So attacker hashes things. What kind of things does he hash? Well, messages. And he gets the values, let's call them a little h, which is hash of m. The trick is that the reduction should operate this hash function. Okay, so we are in a model where h is modeled as a random oracle. So it is a box in the sky that any attacker can use to evaluate hashes. But the hashes are, every time you evaluate a hash on anything, you just get a random point in the range of the hash, which is the domain of the trapdoor permutation. So look what the reduction has to do in order to create these fake signatures. It has to kind of invert this function, right, on a point hash of mi. Well, let's flip it around. The reduction doesn't invert on these points. It programs these points so that any hash of anything, yes, it will be a random value in the domain, but it will be computed by sampling a random point in the domain. So here is the FPK function. The reduction will pick a random x and program hash of m to be the value of the permutation on the output, on f of x. Will it be a random point in the domain? Yes, because the reduction will pick a random point here, and this is a one-to-one function. So choosing a random x and outputting fpk on x samples a random point here. So these hashes will look random, the ones that reduction gives. So an attacker which expects to see a random function will actually see a random function. For any m, the reduction internally will sample x and define hash of m to be fpk on x. If the reduction does that, then whenever adversary asks for a mi, without loss of generality, reduction, if this was never hashed by the attacker, then the reduction just hashes it itself. So you're going to assume that any mi here will be pre-hashed. So therefore, hash of mi is fpk on some xi. So the signature is just that xi, right? So the reduction actually had very easy for the reduction to create these quote-unquote inverses of fpk function, because it chose this to be this function computed forward on a random point in the domain, and then when the inverse was, the adversary essentially asked for the inverse of that hash, well, the reduction had no problem supplying it. Well, if all the hashes here are programmed by the reduction by choosing a random sigma I in the space here, so it's just randomly chosen, in this domain, in the message space, and hash of mi is defined to be this is fpk on sigma I. Okay, then this part is no problem. This part will be problematic because sort of okay, let's now forget about the CMA queries. Let's say you only want security against a no message attack. Okay, so you don't have to create these forgeries. You just want to make sure that when adversary forges, He creates an M star sigma star, which has this. Then you can invert this function on a point that was a challenge. What would be your strategy to do so? Well, how about every time adversary hashes anything, embed y into the hash? Well, this would look very different from a random oracle because every time you hash anything, you get the same value. Okay, so let's skip that part for a second because that's not good. But let's say that basically hash of any m was defined to be y. Then if somebody forges, then what do they get, right? Like they invert FPK on hash, which was y. So the sigma star is the x. Let's deal with two things at a time. First, well, clearly I cannot program the same y into every hash because then every hash looks the same. Okay, how about you guess the query? You guess one of these queries. So how many of them are there? QH, which is polynomial in the security parameter. So adversary hashes, you guessing one of them, embedding y in the output of the hash. For all the others, you output at random. If adversary cannot tell because y is the random value. So he doesn't know which query you embedded y into. And then at the end, he chose one message. And again, without loss of generality, this m star, if it wasn't hashed, then the reduction will hash it, right? So let's just assume it was hashed. With the probability 1 in QH, the m star here is the same m that the reduction answered with this y. So therefore, this will be y, and sigma star will be x. And that works for probability 1 of QH, but so the advantage of the attacker against the CMA game of the security is the advantage of the reduction against in the trapdoor permutation game will be like this. But if this was 1 over polynomial, this is 1 over polynomial, so this whole thing is 1 over polynomial. Okay. Now, we had a different embedding strategy for what to put in this hash in order to simulate these fake signatures. So to create sigma i's are set h and I to be FPK sigma I for random sigma I chosen in the message space of the space of this trapdoor permutation. To translate message signature into X such that FPK on X is Y, R picks one query, one H query MI and sets hash of MI not in this way, but to Y. And you can basically see that this follows. Because with the probability 1 in the QH, M star is that query. So therefore, if there is, first of all, M star has to be different from all these MIs, right? In order for this attack to be in a successful attack. So you can assume in the successful attack that M star is different from all those. And so therefore, this way of embedding values in a hash didn't really interfere with this way of embedding values in the hash for all the other queries. So all the other hash queries will be answered in this way, and therefore reduction will have no problem creating fake signatures on it, or in fact valid signatures on it. And if adversary does forge on this message that we guessed, that the reduction guessed, then sigma star is the X, right? Okay, so that's the argument. Okay, so I mean, I should have known that there is no way I can you know, do that and introduce zero knowledge proofs to start explaining ECDSA. So that will be next time. And we have only a few minutes, so maybe I will stop recording